Welcome back to Chapter 3 in Statistical Reasoning. We're going to finish up the chapters today, and our last section deals with measures of relative standing and box plots. So we have to have some way to be able to compare data that doesn't necessarily come with the same measurements or units of measure. And so to do that, we do what's called a z-score. And one of the prime examples is if you take both the SAT and the ACT and you want to get admitted to a college, they need to be able to compare how your ACT score compares to somebody else's SAT score, and so they would find their z-score and then they can make a comparison. So to find the z-score, we have two formulas showing on the screen. We have an x minus x bar divided by s. So here we are using this sample data. The x bar is the sample mean, s is the sample standard deviation. In the second one we see here, we're using population information. The mu is the population mean, and the sigma is the population standard deviation. Z-scores are rounded to 2 decimal places no matter what. That is what we're going to use. Important things about the z-score. The z-score tells us how far above the mean that a number is in standard deviations. It is expressed with no units because it's just how far something is. And we're still going to use the idea of significantly low or significantly high if it is more than 2 standard deviations away, either below or above. Your z-score will only be negative if it is lower than the mean. So here's an example, and we just want to know which one's more extreme. In other words, which one is farther away from the mean. So we're going to do our z-score formula. So on the top one here, we'll do that one here on the left. So z equals your actual data value. We have a 4,000 gram weight of a baby. So that's our value. We are going to minus the mean. It says the mean is 3152. And we're going to divide by the standard deviation. So on our calculator, 4,000 minus 3152, and then divide that answer by 693.4. I get 1.22295. So to 2 decimal places, 1.22. So it's a little over 1 standard deviation above the mean, which makes sense that it's above because 4,000 is more than 3152. Now we're going to do it for the other side. So z equals, now we're doing the temperature one. The actual temperature is 99. We're minusing the mean of 98.2. We're dividing by the standard deviation of 0.62. This actually should have been an approximation because I rounded. And now we're dividing by 0.62. To 2 decimal places, 1.29. So the temperature information is more extreme than the baby weight information because it's a little bit more farther away. The 1.29 is a little bit higher than the 1.22. But in actuality, neither one of them are statistically significant because neither one are above 2 or below -2. So here's an example dealing with platelet count. The lowest platelet count was 75. We want to know, is that significantly low? The mean is 239.4 and the standard deviation is 64.2. So z equals the number we're focused on, which is 75, minus the mean, divided by the standard deviation. It is below the mean, so we're going to have a negative number. So negative 164.4 divided by 64.2. So our z is approximately negative 2.56. So is this statistically significant? Well, if we're using the fact that if it is less than -2 or more than 2 than it is, Since this is less than -2, we are saying it is statistically significant. Percentiles are another way that we can compare different people taking a test or different tests. The idea with a percentile, you probably, when you took one of those standardized tests, it said you got the 90th percentile, the 10th percentile, the 50th percentile. What that means is that if I was talking about the 80th percentile, you did better than 80% of the people, and 20% of the people did better than you. So it's only comparing those that took the test. To find your percentile, you find out how many test scores were less than yours, and then you divide it by how many there were total, and then we times it by 100 to turn it into a percent. So in this situation, we're still dealing with the Verizon cell phone data speed. It wants us to focus on 11.8 megabytes per second. So I'm going to find that on my chart here. Oops. So here's my 11.8. I'm going to find out how many were below. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2 rows of that, so that means there's 20. So it's 20 divided by how many total there were. That's 50. And then we're going to times it by 100. 20 divided by 50 is 0.4. 0.4 times 100 is 40%. So the percentile that we have here is the 11.8 megabytes per second is the 40th percentile. So it is better than 40% of those data speeds, but yet 60%, which is the other part of the 100%, are better than it. So our notation, N is the total number of values, K is the percentile being used. I like showing the example there that it is for the 20th percentile, our K is 25. L is the location, and then if you can see if there's a P with a little number below it, that means it's the 25th percentile. So here's a table that it is good for you to have. It is also in your textbook if you want to reference it. It helps you move through the steps because there is a junction down here with the gold diamond, and depending on what your answer is here, if you move to the right or if you move down. And we'll use this and I'll refer back to it. So here's the question. It wants us to find the 40th percentile. So if we look at this chart, it says sort your data. That's done. We're going to compute L equals K over 100 times N. So I'm going to rewrite that on this paper so we can, this page so we can see it. L equals K over 100 times N. So if we look here and remind ourselves, K is the percentile in the equation, or in the question, and N is the number of values. So it's asking us the 40th percentile, so K is 40. N is 50, so 40th percentile times 50, so that is 0.4 times 50. 0.4 times 50 is 20. So it says, is L a whole number? 20 is a whole number, so the answer is yes. So the value of the kth percentile is midway between the 11th value and the next value in the sorted set of data. Add the 11th value and the next value and divide the values by 2. So we're going to go find the 20th, and it says the next value in the sorted data. So the 20th number is actually 11.6. So it says take that number and the next one, so 11.6, the next one is 11.8, and we're going to add them up and divide by 2. So 11.6 plus 11.8 divided by 2 is 11.7. So we would say the 40th percentile is 11.7. Notice it's a little bit different, and it's all in that idea of if you rounded or not when we're dealing with percentiles. So percentiles break things into groups of 100, and so we have quartiles now, which break things into quarters or groups of 25%. The first quartile is the lowest 25%. The second quartile breaks things into 50 and 50. The third quartile breaks the lowest 75% from the upper 75%. Some of the other terms that are in this section is the interquartile range, that is the Q3 minus the Q1. The semiquartile is Q3 minus Q1 divided by 2. Midquartile range, Q3 plus Q1 divided by 2. And the 1090 quartile range, notice they've switched back to the percentiles, percentile 90 minus the percentile of 10. So we're no longer dealing with quarters anymore. We have what's called the 5-number summary. It's another way to represent data. It's used most of the time whenever you decide to find the median versus finding the mean. The first number in the 5-number summary is the minimum, and then the first quartile, the second quartile, the third quartile, and the maximum. Notice the second quartile is the same as the median. So here's our set of data that we're going to work with. And so when I'm doing the 5-number summary, I think it's easiest to start in the middle. So let's find the median first. So I have 50 numbers, and so 50 divided by 2 is 25. So I'm going to find the 25th number. So 10, 20, 21, 22, 23, 24, 25. Now, is that really the number? So if I think about it, I have 24 numbers that way. 10, 20, 1, 2, 3, 4 numbers that way. It's an even group. So if I think about back to the median, if I have an even number of numbers, I'm going to have 2 in the middle. So I do. I have 13.7 and 14.1. So our median is going to be those two numbers added up and divided by 2. And I'm going to get 13.9. So now that I have the median, which actually falls here in the group, I need to find the quartile 1. So to find quartile 1, I'm going to take all the lower data, so that's everything below 13.7, and I'm going to find the middle of that group. So I have 25 numbers. If I try and find the middle of 25 numbers, I'm only going to have a single number in the middle. That's not handy. So I've got 10 there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now I'm just looking at these 5. So I just start finding the one in the middle. So the middle will be 7.9. Now I'm going to do the same, but I'm going to do it for the upper group. So I'm here, and this is now my lower 25 numbers. Again, I have the bottom 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here's the 5 numbers in the middle. Start finding the 1 in the middle, and it's 21.5. So that is quartile 3. So I've now found the median, which is the second quartile, the first quartile, and the third quartile. I have the minimum and the maximum left. Those are just looking and seeing what I have. The minimum, my lowest number is 0.8. The maximum, my highest number is 77.8. So my 5-number summary, 0.8, 7.9, 13.9, 21.5, 77.8. A box plot is a graph picture of showing the 5-number summary. We'll use it using a number line, and then we put some boxes and some lines above it. In previous math, you might have heard it called a box and whisker. It's the same idea. So here's the same set of data. I already have all of my information. I just need to put it down. So let's just rewrite what we know. Our minimum was our minimum was point. Actually, you know what? I don't want to write all of this. Instead, we're going to just get rid of that. And I'm just going to write it as an actual 5-number summary normally is written, which doesn't mean you'd label it. You just put it in order. So it's 0.8, and then it was 7.9, 13.8, 21.5, 77.8. So I'm just going to verify those numbers real quick. 0.8, 7.9, 13. Oops, so it's 13.9, not 13.8. So let's fix that. .5 and 77.8. Okay, so now when we're actually going to make this box plot, we have to be the same all the way across our number line. We can't change its value. So since my first number is so low, I'm just going to start at 0. And 77.8 is my maximum, so I'm going to make my life easy and just start at 80. And then I'm going to break this up. That's 40. That would be 20. That would be 60. 10. 30. 50. 70. So I'm trying to do the best thing I can and just be as accurate as possible on a sketch. So let's just start in the middle. So my medium is 13.9. That would be 15, so 13.9 would be approximately there. 7.9 would be a little bit below the 10, and of course 0.8 is all the way down at the end. Then I have 21.5, which is a little bit more than 20, and 77.8 almost all the way to 80. So what you do is the two quartiles in the middle, so this one here is quartile 2, right, and quartile 1, that's 25%, 25%, and then I have this line and this line. So that is an example of what a box plot looks like. I can see that most of my data is really low in this area, and so there's this idea of skewness which is coming up, and this is definitely skewed. It's skewed to the right because most of my data is on the left and I have what's considered a tail moving to the right. Skewed data is not symmetric and it extends more in one direction than another. There's this idea of outliers or extreme values, which we've been talking about throughout the course of this chapter, but we haven't actually figured out how to determine if something is an outlier or an extreme value until now. So when we're doing that, notice we have to have Q1, Q2, and Q3, which we do. We're then going to find the interquartile range, which is Q3 minus Q1. We're going to multiply it by 1.5, and then we'll find any upper extremes or lower extremes. So our Q3 minus Q1. So Q3 was 21.5, Q1 was 7.9, so 21.5 minus 7.9 is 13.6. Now we're going to do 1.5 times that. And I get 20.4. Okay, so now to find the outlier, I have an upper outlier limit and a lower outlier limit. So let's do the lower. We're going to take Q1 and we're going to subtract this new number of 20.4. So Q1 was 7.9. We're going to minus 20.4. And I can see that I'm already going to get a negative, which isn't possible as far as actual data speeds. So it would not be considered an outlier or an extreme value unless it was lower than negative 12.5. It's not going to happen, so we don't have any lower extremes, which makes sense because we had a lot of data on the lower end. Now let's do the upper. So our upper would be Q3, which was 21.5. And now we're going to add the 20.4. 21.5 plus 20.4, that's 41.9. So anything above 41.9 megabytes per second is considered extreme. We definitely had that. We actually, if we look back at our original numbers, so 41.9 and above is extreme. So we actually have 4 numbers that are considered to be extreme. 43, 55.6, 71.3, and 77.8 would be considered extreme. So then what we have is this idea of a modified box plot. And the idea here is that it actually shows us any extreme values within the box plot. So I'm just going to go back to my box plot before, and we're going to turn it into a modified box plot. So the idea here, the only difference is these extreme values, instead of just looking as part of a line, they actually have symbols that represent each one. So 77.8, I would mark with a star, or some people just use it in a large dot. You would do 71.3, 55.6, and 43. So all 4 of those end up being some kind of special symbol. And then what happens is your upper line here only goes to the next highest value, which in this case is 38.5. So I would stop there, and so my line would only go to this 38.5, and the next 4 would just be symbols instead of an actual line. So the red is, in addition with the bottom part, is the modified box plot. And so not only do you have to be able to make one, you have to be able to read one. So go ahead and look through the assignment for this section. We have finished chapter 3. If you have any questions, please let me know, and I will get back to you. Thank you and have a good day.